All right, so today is 12/20/16, and we're talking bonding. So we've got our handy little chart up here. 0 to 0.3 is what we said? This is nonpolar covalent, and these are, of course, differences in electronegativity. 0.3 to 1.7 is polar covalent, and 1.7 to 3.3 is ionic. Okay, so now we're going to examine beryllium and carbon. You've got your chart of electronegativities out. Go ahead and look them up. 1.5 for beryllium. What do you have for carbon? Jaden? 2.5. So the difference in electronegativity is 1, which does put it squarely here. Now the question is, what does that look like? And what that looks like, and carbon, we're going to talk a lot more about how carbon bonds, but carbon tends to form, well, if we had something that was just beryllium carbide, what that would mean, so remember we looked at chlorine and bromine, and they had a very subtle difference in electronegativity. It was pretty much nonpolar. They're sharing the blankets, they're sharing the electron cloud pretty evenly. When we look at beryllium and carbon, which one is more electronegative? Carbon. So when we look at that electron cloud, instead of being pretty even like that, it's going to hug beryllium and billow out a little bit around carbon. Carbon is basically going to pull the electrons towards itself. So it's hogging the blankets, so to speak. Let's look at a few other examples. Okay, so we see that in this case, beryllium kind of hogs the blanket. So let's look at a couple of other instances. Get rid of that. So let's look at a few other things here. Nitrogen and oxygen. These form various nitrous oxides. Emissions from a lot of vehicles have what are called NOxes in them, NOx, meaning it's nitrogen and some number of oxygen. So they're bad. They don't do good things. So what's the electronegativity for each of them? What's the electronegativity difference? 3.0. Lucas, give me oxygen. 3.5. Difference of 0.5. So, when nitrogen and oxygen are bonded, and this is pretty subtle, so if that's a sort of evenly distributed electron cloud, what we're going to see is just a little bit more cloud around oxygen. So this one, it's 0.5. It's subtle. It's not terribly polar, but they're not totally sharing evenly. Oxygen is pulling a little bit more of the electron cloud towards it than nitrogen is going to have. Give me the electronegativity for phosphorus, Lauren. You got phosphorus. 2.1, and oxygen we said was 3.5, so what's our difference? 1.4. This is pretty darned polar. This is strongly polar. So when we see phosphorus and oxygen, phosphorus is not going to have much of the electron cloud. It's going to sort of cede most of that cloud to oxygen. What that ends up doing when we have a polar molecule, we've got an idea of what polar molecules look like. What does this mean in practicality? What it means is that when we have a polar molecule, and we'll take this one as an example, more electrons are over on this end of the molecule. What's the charge on electrons? Negative. So it means that overall, this end of the molecule has a slight negative charge. It's called a partial charge. This has got a bunch of protons in the center, and most of the electron cloud has been pulled away from it. That means that overall, that end of the molecule has got an area of slight positive charge. So polar molecules have these areas of partial charge. They have poles. And if you think about, the Earth with the north and south pole, they're just opposite ends, opposite, in this case, magnetic fields, and that's what a polar molecule means. It's got some implications when we get into solvents. Polar solvents tend to dissolve things that are polar, so polar and nonpolar. Okay, so this is just what we were talking about. In a non-polar covalent bond, and we said, what, like chlorine and chlorine, identical, totally non-polar, purely covalent. There is no area of overall defined charge on this. The negative charges are all spread out evenly. The positive charges are all in the center. So if we look at the whole molecule, it is bound together and it is neutral. There is no area of partial charge. In a polar molecule, we end up with these little partial charges, positive and negative charges on the ends, just because of where the electrons end up. So it's important here to make sure we define the word molecule. A molecule is neutral. So a molecule has no charge. Some molecules are polar and therefore they have regions of charge, but overall they're neutral. And molecules are held together with covalent bonds. If it's not covalently bound, there are no molecules, period. When we have something that's held together covalently, so the simplest units are molecules, that's called a molecular compound. And we'll start to distinguish between molecular and ionic compounds and metallic compounds. And we'll actually be doing a lab right when we get back that looks at the characteristics of molecular versus ionic solids. For each of the pairs given here, I want you to look up the electronegativities for each, look up the difference, and write what kind of bond they would form. Go. So just to review, you had 0.9 for sodium, 3 for chloride, difference of 2.1, so you're saying it's an ionic bond. Would there be a molecule of sodium chloride? Is there a molecule of sodium chloride? A molecule is a group of atoms whose atoms are held together by covalent bonds. There are no molecules of sodium chloride. Period. They don't exist. It is a trick question. I will ask you about molecules of ionic compounds. They don't exist. So just I'm warning you of the dirty, evil, nasty tricks that lie in store for you. Good. Okay. Who's got the next one? Either one, hydrogen and oxygen or boron and fluoride. Who wants to take it? Okay, so we have hydrogen with 2.1, oxygen with 3.5, difference of 1.4. That makes it a polar covalent compound. And what's a common substance that we know that's formed from hydrogen and oxygen bonded together? It's all over the place, water. So water is two hydrogens sort of perched atop an oxygen. It's often called Mickey Mouse because little water molecules look like little Mickey Mouses. Water is a polar molecule. Oh wait, I gave it away. So, are there molecules of water? Yeah, give it away. There are molecules of water, and they are polar molecules. And what we find, so which of these substances in that bonded triad of atoms would pull the electron cloud more strongly? Oxygen. Oxygen's pretty electronegative. So in fact, what we see is that the electron cloud around hydrogen gets sort of pulled down tight, and much more of the electron cloud ends up residing around oxygen. What this ends up meaning is that Mickey's little ears are positive. I always think of Happy Mickey. Some of you were just at Disney. Little ears are happy. Mickey's little chin is negative. So the oxygen end of the water molecule has got this region of partial charge. That's important. That's one of the reasons water is such a great solvent, is because it's polar. Okay, B and F. Okay, boron and fluorine, difference of 2, it is ionic. Are there any molecules of boron fluoride? No, it's ionic. There are no molecules. Here's an important point. Now, next chapter we'll be doing formula writing, and we'll start the math that comes along with that. You have used chemical formulas. You haven't named them or written them much. But the thing to understand at this point is that there are two different naming systems. So there's a naming system for molecular compounds, and there's a naming and formula writing system for ionic compounds. Ooh, boy. And you have to be able to look at a compound and distinguish if it's ionic or covalently bound so that you get the name right. So with molecular compounds, and that's the one that we're going to talk about first, the formula actually tells you, using prefixes, how many of each atom there is. So we have, carbon monoxide, 1 carbon, 1 oxygen. Carbon dioxide, 1 carbon, 2 oxygens. We also see diatomic molecules that are molecular. So oxygen binds to oxygen. You know the Heavenly Seven. We talked a little bit about this. We'll talk more about it next chapter. Oxygen, nitrogen, hydrogen, fluorine. Let's see, oxygen, hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. That's only 6. There's one more that I always miss. Nitrogen, oxygen, hydrogen, fluorine, chlorine, bromine, iodine. No, that's 7. Never mind, I got it. Can't count. So we see diatomic molecules, and those are molecularly bound. What kind of bond would we see in O2 without thinking or doing any math? Oxygen bonded to oxygen has an electronegativity difference of 0. What's the bond type? Nonpolar covalent. Yeah, it's as purely covalent as you can get. They are sharing 100% equally. This is equal sharing. Okay, so here's where we have some serious life analogies. When's homecoming? 14th of January. Okay. Some of you probably have dates to go to homecoming. Some of you are probably going to go hang out at homecoming with somebody who you think is really swell. Maybe there's that person who you've always had a crush on. We'll call them generically Cutie Pie. And, you've been sitting in class with Cutie Pie since whatever, kindergarten, 1st grade, 5th grade, when they magically moved here from the Kingdom of Wonderful, and they showed up in your world, and you were like, oh, Cutie Pie. Your attraction to Cutie Pie is strong. You would like to sit next to Cutie Pie. Like to talk to Cutie Pie. Probably like to dance with Cutie Pie. It's all good stuff. Ride around in cars with Cutie Pie, do whatever, Just being next to Cutie Pie. There's a problem, however. Cutie Pie has a best friend who you find to be the most repugnant, repulsive, offensive, disgusting human being on the planet. You'd rather not be in the same room with best friend because best friend is frankly just awful. Awful! Intellectually and morally bankrupt, offensive, smelly, I don't know, trailing excrement, I don't know. Best friend is just horrendous. So you end up in this sort of approach avoidance situation. There's another psychology term, approach avoidance conflict, between your love of Cutie Pie. Cutie Pie! But everywhere Cutie Pie goes, guess who follows? Best friend. So there's Cutie Pie. Cutie Pie! You go racing to Cutie Pie. And you get about so close to Cutie Pie, you can smell best friend. Mention best friend stinks. So you get about so close to Cutie Pie, and then, you hit that wall. That wall of absolute repulsion for best friend. It was awful. Just awful. This is the process of forming a covalent bond. I kid you not. So, Cutie Pie is that oppositely charged particle. So when we have two atoms that are coming together to form a covalent bond and share electrons, there is a powerful attraction between all of the little electrons in one atom. You know, here's our, well, let me make a fuzzy atom. So within each atom we have this little positive nucleus. And this little positive nucleus is very attracted to those electrons. Woo-hoo! Cutie pie! But the problem is this. Well, and you know, likewise, this positive nucleus is strongly attracted to these little electrons. Love, or at least strong electromagnetic chemical attraction between those charged particles. The problem is, what color could we make this that would make it obvious that this was repulsion? Bright red for danger? Okay. Okay, so when we have two atoms that are attempting to bond, what you've got is a dance between the protons being attracted to the electrons in the other atom and those two nuclei being strongly opposed to interacting with one another. And these electrons are also opposed to interacting with one another. So we have forces of attraction, we have forces of repulsion. So we have the attraction between the protons and the protons and the electrons, that racing towards one another, being pulled like two magnets, two things that are attracted to one another, pulling together. There is energy in that attraction. And then when they hit the distance where suddenly these electrons are like, oh no, I cannot be in the same room as you. I cannot be this close to you, because they're repelled by one another. These protons hit that wall where they're repelled. And there's another force that starts up, and that force would start to shove those things backwards away from one another. The point where the bond is formed is where those two forces are totally balanced. So at the point, okay, so there we've got the forces of attraction, the forces of repulsion. So if we think about this in terms of energy, because we really want to think about all this stuff in terms of energy, because atoms are all about potential energy. When you have two things that are strongly attracted to one another, and they're being held apart by something, there is a force that's going to pull them together. They're not stable there. And you can think about, I keep going back to this, a rock on a hill, this marker held up in the air. Is this marker attracted to anything? Every time I let go of it, it goes racing towards the center of the earth, which it finds ever so attractive. It's not stable up here. It's high energy because it's strongly attracted to the center of the earth. And the minute that I take out the obstacle holding it away from the center of the earth, it falls. So these two atoms, when they're being held apart, well, let me actually get that a little bit more like that. When they're being held apart, they're strongly attracted to one another. They're unstable. They're high energy. The minute you let go of them, what's going to happen? They're going to start pulling towards one another. Great, and their energy is going to dip. But when they get about so close, guess what happens? That repulsive force kicks in. And if they're too close, well, let's see. Let's make these more like, they're a little bit apart, because if they got too close, like if they were smooshed right up against one another, their energy would actually be higher, because that repulsive force would be starting to kick them back out. So it's kind of like this rubber band effect, where they want to be close but not too close. Okay? Bonds form at a distance where attraction and repulsion are minimized, where the atoms are at the lowest possible energy, where attraction and repulsion are balanced, and that energy is minimized. They're stable there. So when these things share electrons, and oxygen, actually let's go ahead and we'll use the oxygen-hydrogen model instead. Sorry about that. So hydrogen would like to have a full outer level. Its uppermost occupied energy level is, you can answer this with fingers. 1, 2, 3, 4, 1. How many electrons would fill the first energy level? 2. So hydrogen would like to feel like it's got 2 electrons on the uppermost occupied main energy level. Oxygen would like to have a full uppermost occupied main energy level. What's its uppermost occupied main energy level? 2. Yep, it's as simple as you think it is. How many electrons does oxygen have on that level? 6. And we know that because it's in group 16. In the P block, the number of valence electrons, that's uppermost occupied main energy level electrons, are group number minus 10. We also know that because if we start filling these in, we put 2 on the first level, that's all it can hold. We have 6 left over. Oxygen would like to have how many on that second level? 8. Well, what oxygen does is it gets that by sharing with hydrogen. So these guys are both actually holding those electrons. And their electron clouds are literally overlapping. So these electrons have the ability to flow over into oxygen, to flow over into hydrogen. Now we know because oxygen is much more electronegative, where do they hang out? They hang out closer to oxygen or closer to hydrogen? Closer to oxygen. Because oxygen's more electronegative, it has a better ability to attract electrons towards itself when it's part of a bonded pair. This is the cool kid on the block where like everybody wants to hang out at Joey's house because Joey's mom lets everybody drink pop and swear. That's where everybody wants to hang out. The electrons all want to hang out nearer to the more electronegative element. So they're sharing, it's true, but oxygen's getting most of the benefit. And hydrogen's okay with that. It doesn't really need the electrons. If it could get rid of them completely, it would, and it very often does. It very often forms a +1 ion. Okay, correction. We're going to stop. I'm going to assign some this is chapter 6, homework problems, and let you work. Okay, so chapter 6 homework, this is the chapter 6 review, page 195. You've got numbers 2 through 11 to get started on, and you've got a good solid half an hour. You can probably actually get most of those. That's it.